Hello again, and thank you for joining us on another episode of Space Nuts. My name is Andrew Dunkley, your host. It's great to have your company. I hope you're well, and I hope you can stick around. We've got some really great stories today. These are fascinating. Remember that asteroid impact that led to the loss of the dinosaurs? Happened a couple of weeks ago. It may have been much worse than we first thought. Lots of crispy critters as a consequence. We'll explain all that. There was a near-Earth asteroid discovered around 30 years ago. Well, now new evidence suggests it may have been a comet. And I love this story. This is about a Canadian amateur astronomer who was planning a trip online using online maps. And he made a massive discovery. We'll tell you all about it on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us this time around with Fred gallivanting around chasing solar eclipses is Professor Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Welcome back, Jonti.
Oh, thanks for having me. It's good to be the substitute Yorkshireman again.
Yes, we've got a whole set of them. It's really good stuff. Now, we've got some amazing stories. I know you've been a very busy young fellow for, since we last spoke to you. You do your own sort of gallivanting, but we managed to nail you down for a couple of weeks, which is fantastic. Let's get straight into it because these stories dovetail well. We've got an asteroid that may have been a comet. Then we've got an asteroid that hit Earth that seems to have done more damage than we thought. And then we've got a hole in the ground discovered while someone was planning a holiday. All kind of related. So let's get stuck into the first story. A near-Earth asteroid that was discovered 30 years ago, they think might have been a comet.
Yeah, this is a lovely story, and it ties into something that we've talked about in different lights previously when I've been on the show, and I'm sure Fred's spoken about it quite frequently as well, which is that very human need to break things up into manageable chunks. So you go from being a child to being a teenager to being an adult, and there's a miraculous day when you wake up and you're suddenly legally able to drive.
Yes.
And in different countries, that's a different day, but we all have it. But fundamentally, you're not really any different as a person the day before that and the day after it. What we're doing is we're breaking up this kind of continuum of human experience into chunks where we group things that are similar together and we put things that are more different into separate groups. And I've talked about this in the past when we've talked about the difference between planets and stars and that amazing middle ground that are brown dwarfs, where in effect you've actually got objects of all sizes from the size of a grain of sand, actually from the size of a single atom or a single subatomic particle, all the way up to the biggest galaxies and beyond in this kind of continuum of sizes. But you go through kind of rock to planet to brown dwarf to star, and we put these arbitrary divisions in so that we can group things that look similar together and study them to make life easier. And we talked about that, of course, in the context of Pluto, with the whole thing of when is a planet not a planet, when it's a dwarf planet, and why all that happened. That's exactly the same kind of thing. In my kind of contextualization, that was the right decision. That's a hill I'll quite happily plant my flag on. But Pluto's like the gangly teenager. From a distance, it looks big and like a serious adult, but it's still not very good at tidying its room up. That's the kind of analogy there. This whole story is another one of those same things. If we had been talking 300 years ago, people would have been familiar with comets, at least the bright ones, things that get bright enough to see with the naked eye, that have a glowy coma and a tail.
Yep. They
appear briefly, then vanish forever. And we had great comets a couple of times in the last few years. On average, one per decade, but it's a bit hit and miss. And the idea is, with modern scientific knowledge, what you're seeing when you get that phenomenon is a big dirty snowball or a snowy dirt ball that's whizzing around the sun on this hugely elongated orbit. When it's far from the sun and it's nice and cold, we just don't see it. You'd need the biggest telescopes on the world because you've just got this little thing reflecting a bit of sunlight. But when it comes near to the sun, its surface gets hot. The volatile material on it gets too hot to still be solid, so it turns into gas. And that gas erupts from the surface, carrying with it dust, shrouds that snowball in what's called a coma, a big spherical cloud of gas. And then the solar wind pushes the gas and dust away from the sun and you get the tails. And so a comet, as we see it, is pretty big, can be millions or tens of millions of kilometers across, which is this huge amount of gas and dust floating around in the solar system, all given off by an icy, rocky, rubbly object only a few kilometers across in the head. And that's a comet. So it's basically something that has activity that outgasses as it goes around the sun.
Yep.
In 1801, came along, and Giuseppe Piazzi found Ceres, which was an object between the orbits of Mars and Jupiter. And he found it because they were looking for a planet, because people had suggested that might just be that there's a planet between Mars and Jupiter. So the celestial police were looking, but Piazzi got there first, and that was the first of the asteroids. And over the decades and the couple of centuries that followed, one object became 4 or 5, became tens, became hundreds, became thousands. And nowadays is over 1 million. And if we were talking kind of 30 or 40 years ago, we'd have had a very clear idea of what an asteroid is, and that an asteroid is very different to a comet. So an asteroid is a rocky or metallic object that, even when it gets near the sun, just stays as a rocky metallic object. No gas comes off it, just a lump of rock or rubble going around the sun. So rocky, rubbly object, icy object with loads of gas. You've got a comet, you've got an asteroid. Very distinct. Now, water's got a bit more muddied for a few reasons over the last few decades. Firstly, you had objects called the centaurs, which I studied for my PhD, that are big icy objects that are too far away from the sun most of the time to outgas. So got kind of asteroidal classifications, and a couple of them got a bit nearer in and started outgassing, so got a dual classification. Chiron is the most famous. Chiron has both an asteroidal classification and a cometary classification, because sometimes it looks like an asteroid, sometimes it looks like a comet.
Yeah.
You then have things like the Geminid meteor shower every December, which is our best meteor shower. I love it dearly. Almost all of the meteor showers are produced by comets, and we get them when we go through the dust that has been left behind by the activity of the comet when it was outgassing. But when they found the parent of the Geminids, it doesn't look like a comet, it's an asteroid. So the idea became that maybe it's a rock comet and it's getting so close to the sun, it's shedding dust, and we get the meteor shower. Then there were a couple of comets that were lost, and then many, many decades later, an asteroid was found that looked to be moving on the same orbit as a comet. And so maybe they're the same object and the comet has turned off. And when the comet has turned off and stopped making any gas, maybe it looks like an asteroid. So there's this blurring going on. In reality, what you've got is a continuum from rocky and metallic and nothing else on one end to incredibly icy on the other, and everything in between, where you have more rock, less ice, more ice, less rock, blurring together. That's a hell of a lengthy introduction, a hell of a lot of background to give the context for this story. So in the light of all that, back in 1998, there was this near-Earth asteroid discovered. It goes by the name of 1998 SH2. And it looks like a lump of rock. It goes around the sun every 4 or 5 years, whizzing around. It's been seen at a few apparitions since. And that's all well and good. We know a few thousand near-Earth asteroids now, and we're finding more and more of them all the time. And people are particularly interested because, of course, if they come near the Earth, there's a possibility that eventually one of them will come too near the Earth and will hit us. Yeah. And we'll have issues and, ask the dinosaurs about that. We can come back to that a little bit later on. So there's a lot of interest in learning more about near-Earth asteroids and following them, because the longer you observe them, the more accurately you know how they're moving. So the better you can predict into the future where they'll be, and therefore rule out the chance of that object hitting the Earth. May also, of course, be interesting to people who want to mine that object in the future with off-Earth mining, that if you want to go mine it, you need to know where it is.
Yeah.
So that's this object. Brilliant. We found a near-Earth asteroid. Where it gets interesting for this story is that back in August 2025, which is 27 years after this thing was discovered, it had another close approach to Earth. Now, this wasn't like the forthcoming approach for the asteroid Apophis, which is going to come closer to us than geostationary satellites. This was close to astronomers and distant to everybody else. You're talking about the thing coming about 3 million kilometers away at its closest approach. Now, that's relatively close, but it's not something to get particularly panicked about. That's nearly 10 times as far away as the moon is, about 8 times as far away as the moon is.
Yeah.
But it's near enough that if you want to learn more about the asteroid, what you can do is you can get the planetary radar that they used to beam radar out into space and bounce it off things and get it back.
Yeah.
To try and bounce radar off this asteroid to get an image of what its shape is, to learn about its rotation and figure out how big it is. Because even with the biggest telescopes on the planet, something like this is always just a single pixel. You can't zoom in. So what they did was they got the planetary radar, sent radar out to this object, and missed. A little bit embarrassing.
As you do.
It wasn't quite where it was supposed to be. So based on all those historical observations, you can predict into the future where the asteroid will be, based purely on the gravity of all the planets. It's getting pulled around by the Earth and Venus, Jupiter, everything's pulling and tugging on it. And you can, in a very prescriptive way, run its orbit forward in time and say where it will be in the future. If the only thing acting on it is gravity. But it wasn't where it should be.
Mm.
The fact it wasn't where it should be says something else is happening as well. Something else is happening to push it around. Now, so at this point, sometimes that we get the, oh, well, it must be an alien spaceship thing happening.
Yeah.
That's exactly what's happened in the past with people suggesting there's maybe something more going on. That actually hasn't happened with this one, which is really nice to see. But what that being out of position tells you is that there are non-gravitational forces acting on this thing. Something other than gravity is happening to push it around a little bit. Now, if we rewind to comets for a little bit, I remember when I was a teenager, back in the early 1990s, we had Comet Swift-Tuttle came past. And Comet Swift-Tuttle's a parent of the Perseid shower. And that was kind of a relief because at its previous apparition, Comet Swift-Tuttle had been seen, widely observed, and had been predicted that it would come back in about 120 years. It would come back in the early 1980s. And it didn't show up. Which was a bit weird because this is a bigger and more active comet than Comet Halley. It's probably the biggest of the comets with a period less than 200 years. Pretty epic object. And it came back 10 years late. Now, by the time it came back, people had figured out kind of what was going on, had realized that it was going to be late. But part of the complexity there was that because this is quite an active comet, when it's ejecting gas and dust to space, that process acts like a rocket engine. That pushes it around. So it's ejecting gas in one direction, and that exerts a force pushing the nucleus in another.
Yeah.
And that is not a predictable thing. In that every time a comet comes around the sun, its rotation will be a bit different. Some active areas will turn off and some will turn on. So while you can get a general trend and you can make loose predictions, there's always going to be a bit of uncertainty in where a comet will be in the future because it's got these forces pushing and nudging it around. You know, it's a bit like, I don't know if you could strap a few fireworks to a snowball and throw it up in the air. That's probably not very healthy to do, but you get the same kind of thing. They go off at different times and it'd be pushed around all over the place.
Yeah.
Interestingly, Comet Encke, which is a comet with the shortest known orbital period, has been seen every 3.5 years, 3.3 years for more than 200 years. And we've actually seen its orbital period get shorter and then get longer again as a direct result of the jets on its surface pushing it around. And those jets changing the rotation direction of the comet. Loads of cool stuff there. So with that knowledge, you can look at this object, 1998 SH2. It's not where it's supposed to be. So that suggests that there's non-gravitational forces happening. But whenever people have observed it in the past, it has looked inert. It's looked like an asteroid. What that suggests is that it is active. It's got some outgassing happening, but at such low levels that it wasn't possible to detect them before. So that was a clue. That seems a really likely story. So scientists go away and they do a couple of things. Firstly, they look for pre-discovery observations of this. You know, times when there was a photographic plate made 50 years ago that just happened to have the object in the field of view. So you can get a longer period of knowledge of how it's moved.
Yeah.
And with these really accurate observations, you can tell that it has been misbehaving for a long time. It's getting pushed and nudged around. What then happened was they used some of the really biggest telescopes in the world to take a look at it and detect just a tiny hint of gas being emitted, tiny little wisp. And so you put all that together, and this thing is probably, of all the comets we know in the solar system, the least active. that we currently know of, but it is exhibiting cometary behavior.
Mm.
So it's another object really straddling the boundary. And it's fascinating. It'll be wonderful to learn more about it. But it's fascinating too, because here's a thing that looks like an asteroid, sounds like an asteroid. It does everything you'd expect an asteroid to do, except it's wibbling and misbehaving a bit. Now, if you're finding hundreds and thousands of near-Earth asteroids and you want to know whether the Earth's safe, well, if you see something that's an asteroid, you can predict where it is with gravity. Going forward, the Earth's safe. What this is telling you is that gravity may not be enough. So you can't just say, well, it looks like it'll be safe, we'll stop looking. Because if this object's unpredictable, what about all the other ones we're finding too?
I was about to bring that up. There's got to be more than one.
Oh, absolutely. We've found quite a few of these over the years now in various circumstances. My favourite really is the Taurid stream of debris. We get the Taurid meteor shower every year from about September to December. We've got the northern and southern Taurids. We also get a daytime meteor shower in June called the Beta Taurids. Result is we spend about 4 months of every 12 passing through this enormous broad swath of debris, where on any given night when the meteor shower is active, even at its peak, you'll only see 4 or 5 meteors an hour. The debris is very spread out. But because the Earth spends so long going through it, we get more debris from that stream than all of the meteor showers combined over the course of a year.
Mm.
At the core of that is Comet Encke, which is that comet with a 3.3-year period, but also a huge amount of other rubble and debris. There's lots and lots of asteroids, or things that behave like asteroids, moving around in the Taurid stream. And the idea is that this was a megacomet 20 or 30,000 years ago that fell apart, giving us this stream of debris. Comet Encke was probably behaving like an asteroid if you'd found it 1,000 years ago, but something happened 250 years ago to wake it up, and it started behaving like a comet, and we see it as a comet. The other asteroids in that stream are currently dormant, and there's a load of them. So it's likely in the inner solar system that even just in the Taurid stream, you're going to have hundreds, if not thousands, of objects just like 1998 SH2, that straddle that boundary between the comet and the asteroid.
Fair enough. And as a consequence of that, they've had to rename it.
Yep, so it now has a cometary classification as well. What happens with comets is you get, when people find a comet, it's C/ then the year, and then a catalogue number. So basically every comet gets a unique identifier. So we remember Chuchinshan Atlas, which I'm trying to remember the correct ID for it, but it was, I think it was like 2023 A1 or something like that, A3. So the A means it's discovered in the first fortnight of the year. 3 is the third object found in the first fortnight of the year. That tells you about the comet, and then it's named after the discoverer in brackets. If the comet is seen at more than one apparition, the C gets changed to a P to show that it's periodic. In this case, because this already has an asteroidal name by which it's known, it's kept that, but they've added a P in front of it. So it's gone from being 1998 SH2 to being P/1998 SH2. It will be interesting to see whether down the line they add the name of the discovery facility to it. That wouldn't surprise me. That's been done for previous occasions where we've had an asteroid that became a comet. But it'll be interesting to see. But I guess what I love about this is you get into the nitty-gritty of it, but it's that reminder of the beautiful complexity we've got. There's so much more to learn.
Absolutely, yes. It's a really good story and one worth reading up. You can do that at space.com, or you can read the published findings in the journal Nature Astronomy. This is Space Nuts with Andrew Dunkley and Professor Jonti Horner. Let's take a short break from the show to tell you about our sponsor NordVPN and to discuss your online privacy. Because let's face it, these days, whether you're browsing at home or jumping onto public Wi-Fi at a cafe or an airport or wherever, your data is constantly at risk. Hackers, trackers, even companies you've never heard of, they're all trying to get a piece of your digital life. And that's where NordVPN comes in. Our sponsor is fantastic. It's one I've been using for many years now myself, and I have absolute faith in their product. NordVPN encrypts your internet connection, hides your IP address, and keeps your personal information safe from prying eyes. It's like putting an entire online world inside a secure tunnel. They've got over 7,700 servers worldwide. You can browse fast, safely, and without restrictions. Plus, features like threat protection and ultra-fast speeds with Nord links mean you're not sacrificing performance for security. You get both. Right now, you can grab our special Space Nuts deal and get 4 months extra for free. Plus, there's a 30-day money-back guarantee, so it's completely risk-free to try. Just head along to our special URL, nordvpn.com/spacenuts. That's nordvpn.com/spacenuts, and don't forget to use the code SpaceNuts. That's nordvpn.com/spacenuts. Stay safe, stay private with NordVPN, our sponsor.
The crew of Artemis 2 now bound for the moon. Humanity's next great voyage begins.
Space Nuts.
Let's move from a comet flying through space to a comet, or an asteroid in this case, that stopped flying through space because a big planet called Earth got in the way. And the one that is referred to as, or creating the Chicxulub crater in what is now known as the Gulf of Mexico. And we even know the exact impact point because they've been down there and taken samples, which was a very exciting story when we covered that some time back. But now they've taken another look at this and gone back to the very moment of impact and the few hours afterwards and decided, by the look of it, that this thing was much more brutal than we first envisaged.
Absolutely. And this kind of ties in with the stories that were told, again, back when I was a teenager. I remember hearing about the impact that killed the dinosaurs and stories about what would have happened on the other side of the planet and the idea of firestorms. And, it was a hellish experience worldwide. But the way you'd normally hear this story relatively recently is you had the impact. Things were bad in the vicinity of the impact. Shockwaves went out, tsunamis went out. So over a very large area, it was immediately fairly devastating. But there was a huge amount of dust and debris flung up into the Earth's atmosphere, which led to this prolonged nuclear winter type event. It blocked the sun, got really cold, the plants died, the animals died. Then when the clouds cleared, it got really, really nasty because you got this period of runaway global warming and hideous acid rain because the impact had hit rocks that were packed with carbonate and sulfate rocks, which led to carbonic and sulfuric acid rain. It led to an atmosphere super loaded with greenhouse gases. So it basically made the planet fairly hellish for a few tens of thousands of years, from one stage to the next to the next. But when I was younger, there were these stories about, there were probably global firestorms, the idea that an impact halfway around the world could set fire to forests elsewhere.
Yeah.
And in recent years, I've not heard that story told so much. It's kind of fallen a little bit out of fashion. But the new research that's been done here is kind of bringing that idea back into the picture. Now, the idea here is that you get this impactor that was probably about 10 kilometers across, smacking into the Yucatan Peninsula, creating a crater that was 200 to 300 kilometers in diameter. In doing that, it would have flung a huge amount of rocky material, vaporized material, out of the atmosphere, and a lot of that material would have traveled at speeds slower than the Earth's escape velocity to rain back down into the atmosphere. And when that material falls back into the atmosphere, it's traveling at speeds of kilometers per second, so it ablates like a fireball that we see in the sky, like a meteor. But you're not seeing one or two, you're seeing a huge deluge of material raining down all across the planet. Now, when these bits of material hit the atmosphere and ablate, what they're doing is they're taking the kinetic energy of their motion and turning it into heat and light. Which, if you get a single small meteor, you're not going to get sunburn from it. If you get something the size of the Chelyabinsk impact, people actually did get sunburn from that, from the brightness of the flash. Now, imagine instead of having one Chelyabinsk impact, having this rain of material falling into the atmosphere all across the planet, creating this, what's described as a thermal pulse. That has been discussed, and previous models, things that have come out, suggested that that effect would have been like putting a grill on. It would have been really quite unpleasant for thin-skinned animals that were exposed to it. You'd have got burned, you might even have got killed. But if you were underground or you were underwater, you'd have been able to live through it. I mean,
Yeah.
you'd have lived to see all the other horrors that were coming from the impact, so it wasn't really a good news story, but you'd have probably survived it. But the argument had been that that thermal pulse from that material coming into the atmosphere would not have got things hot enough to ignite things like grasses, the tinder that you get that can start forest fires and things like this, which I think is why that idea of the global firestorms had gone away. What the new research has done is looking at fossil sites in North America, which must be remembered was quite close to the impact, relatively speaking on a global sense. They've found this layer of spherules of material, which is a debris that rained back down to Earth in the fossil record. And above it, there's this very thin layer of silicate dust, which must have fallen out at about the same time.
Mm.
Now, the idea is that that silicate dust would have effectively acted like a bit of a doona, with that raining down and that in the atmosphere. The fact that it's fallen in the fossil record above the spherules means the spherules got to the ground before the dust got to the ground, effectively. So the researchers have said, well, what would happen if you had all this dust, all this silicate dust in the atmosphere, and you had these spherules raining through, giving off all this heat? And it's effectively like that dust in the atmosphere would have acted a bit like a reflecting blanket or something like that. It would have trapped even more of the heat in the atmosphere and reflected it back down at the ground. And the calculations that they've made suggests that that extra energy, because of the energy being re-radiated back down to the ground rather than escaping to space, would have made things hot enough for grass to catch fire, for pine cones to catch fire, not for an entire tree to burst into flames, but for all the tinder that was lying on the ground to be caught aflame. And if that happens, what you do is you trigger global firestorms. So you turn a situation and you make it much, much worse. Now, what should be said here is that this work is looking at North America, and it strikes me that further away from the impact site, you probably wouldn't have got the impact dust. So it might well be that you actually had a gradiated kind of level of nastiness from the impact. Yeah. So nearby it was brutal, and then you had the tsunamis and stuff washing out. On the far side of the planet, you probably didn't get the silicate dust, so you just got the normal level of hellishness, where you didn't set off firestorms, but things were nasty. But there was probably this sweet spot, like the ultimately bad porridge in the Cinderella story, where things were ultimately worse, as bad as they could be, where the impact way over the horizon, way in the distance, was enough to trigger forests to burst into flame because of igniting the tinder, enough to cook animals alive as they were on the surface. Really kind of brutal and remarkably horrific imagery. But it's fascinating work, and it's another insight into just how bad impacts like this could be. It's that whole thing that we're playing with a detective story that is 66 million years old, and we're trying to piece together the narrative of what happened. And every bit of information we get like this just seems to make a more and more horrific picture.
Yeah, I mean, the original consensus was the asteroid hit the planet, and it created tsunamis that went around the world 3-4 times, something like that, and created the equivalent of a nuclear winter, and everything died, and there was no food, and the creatures died along with it over a period of time. But this is suggesting that a lot of the initial death due to these firestorms happened in a few mere hours. It's a horrifying thought.
It is. And I mean, you start getting to that kind of philosophical side of things. Does this make it better or does it make it worse? If you were there at the time, would you rather be broiled and baked and cooked quickly, or left to starve slowly in the cold that followed? I mean, it's all fairly bleak, but it is also that reminder, just a bit like we were talking about in the previous story, we are in the crosshairs. This will happen again. It's not like the Earth has been hit for the last time, unless we do something about it. And it's great that we have the capacity to discover objects further and further from the Earth with a greater and greater lead time before they come close to us. It's great that we're learning the capacity to deflect them, but it's sometimes hard to justify to people why people are doing this kind of research. And it's one of the arguments we have, for example, against the satellite megaconstellations.
Yeah.
Because we're finally a species that can look out at the cosmos and detect threats. And what we're doing is we're throwing tinsel in the way and hiding the view.
Mm. Yeah, and that is a bit of a worry. Well, it's a big worry, and it's not getting any better. In fact, it's going to get worse. We'll probably discuss that more in our next episode. But I did notice in sort of looking at this story that some papers or some websites refer to it as a meteorite impact rather than an asteroid. Why would they do that?
This is interesting with terminology, and I'm less uncomfortable with the idea of meteorite impact, asteroid impact being a conflation. The terminology of objects is a weird one, and astronomers have very specific terminology that then gets a little bit confused when you see popular science and you see the news and all the rest of it. When something's floating around in space, nowhere near the Earth, we refer to it as a meteoroid or an asteroid or comet, basically. And we talked about asteroids and comets earlier on and where the line blurs there. The typical boundary between calling a meteoroid and an asteroid is often taken as being about 1 meter in size, but that's just fairly arbitrary. When something enters the atmosphere and it's pushing the air in front of it and it's glowing in the sky, that phenomenon we call a meteor. If it's really bright, we call it a fireball, and that boundary is set roughly as bright as the planet Venus. If we see an explosion at the end, we call it a bolide, and that just means exploding fireball, basically. Yeah. So meteor, bolide, fireball are atmospheric phenomena. You're not actually seeing the thing coming through the atmosphere. You're seeing the gas that it's heated up and excited in the atmosphere. That's what you're seeing as a glow. When it reaches the ground and hits the ground, you call it a meteorite. That's the physical object on the ground or hitting the ground. Now, whether you call something like this a meteorite impact or an asteroid impact, I think it's probably both. You know, technically, the asteroid hits the ground. You could call it a meteorite, but maybe what you should do is have that idea in your head of if it's less than a meter across, you could call it a meteorite. Bigger than that, you'd call it an asteroid. I've never seen clarification on where that boundary comes, because they're terms that are used in different senses kind of thing. So for me, I don't think it's unreasonable to say meteorite impact here, although you're probably pushing the size definition. Calling it an asteroid or comet impact is probably more reasonable. And it might be that if you dug into the physics of it and you were to do an IAU resolution, a bit like we did with Pluto, maybe what you'd do is look at it in terms of the effect of the atmosphere on the object coming in.
Yeah.
So things that create fireballs and bolides in day-to-day life, the atmosphere is much bigger in size than the object coming in, which means wind resistance will eventually slow it down. So the meteorite that we talked about a few months ago that landed on someone's driveway in Canada was traveling at about the same speed that a rock dropped out of an aircraft would have done. It was at terminal velocity.
Yeah.
Its speed was governed by the atmosphere. Whereas with things that are kilometer scale, the atmosphere is essentially not there. It's not going to slow them down. And so I wonder whether there is an argument that you could set up a definition that said, if it's traveling at speed less than supersonic, you'd call it a meteorite impact. If it's traveling faster than that, maybe you'd call it an asteroid impact. But I don't think that there's any official delineation like that. That's just kind of how I think about things in my own head.
No, I like that. That works well. That's probably a good way to think about it. Another interesting story, that the asteroid impact that killed the dinosaurs was a lot more damaging in the early stages than we first thought by the look of it. Plenty of websites and news platforms have picked this one up, not surprisingly, but you can read at the Science Advances website, published in Science Advances. This is Space Nuts. Andrew Dunkley here with Jonti Horner.
0G, and I feel fine.
Space Nuts.
Well, story, Jonti takes us to Canada, and this is a story about a Canadian amateur astronomer who decided to plan a holiday using online maps.
This is lovely. I think we've all done this to some degree. You planning your holiday, planning your road trip. I just had a lovely holiday with the in-laws. And you look at the online maps of your choice that typically have really nice satellite images of the places you're going. and you try and figure out what you're going to see, what you're going to go there. And to some degree, you start browsing around thinking, I wonder if I can see anything unusual. What's it like around there? And that's what happened here. We've got this amateur astronomer going by the name of Joel Lapointe, who back in 2024 was planning his hiking and camping trip I think it's in northern Quebec. It's near a place called Lake Marcel. And he found this unusual looking feature next to that lake. Looks a bit odd on the maps, on the satellite imaging. Now, there is a university in Canada that has a website called Impact Earth that allows people to, as a kind of popular collaborative endeavor for citizen science is the word I'm looking for, to log things where people think they've found impact features. So, being an amateur astronomer, being aware of this, he logged it. I think I found a crater. About a year later, the site, as a result of this report, was explored, visited by a planetary geologist from the university called Gordon Osinski, who went there, took a load of samples, explored around, and confirmed that this really is an impact feature. It's an impact crater about 390 million years old, so way older than the impact that killed the dinosaurs, about 25 kilometers across, which includes a load of incredibly well-preserved features in terms of glassy, hardened, volcanic-type rocks from the impact that he himself has said he's surprised they're that well-preserved given how old it is and how far north this is, how cold the weather gets in the winter and stuff. Now, this makes it the biggest crater found on Earth since 2018, when there was a crater discovered under the Greenland ice sheet. But the difference is that the one under the Greenland ice sheet is below a kilometre's depth of ice. So it isn't like we can get there and learn much more about it. That's still quite a mysterious spot. Whereas this is open and exposed and accessible. So people are able to go there and explore it, learn a lot about it. There's some really nice imagery out there on the internet about this, from the maps images where it was found to images of features called shatter cones, which are the kind of thing created that are very typical of an impact crater formed under very high pressure and very high temperature, molten rock. So it is absolutely amazing. But it's also, to me, kind of breathtaking that here is a feature 25 kilometers in diameter in the middle of a built-up, well, not that built-up country, but in the middle of a country near a famous lake that is an impact crater that had never been identified until now. You know, we're still discovering kilometers, tens of kilometer scale features on the Earth. I mean, that's just astonishing.
Yeah, it is. And I think we've talked about it in the past, that one of the problems with finding these things on Earth is the fact that Earth's kind of covered up with vegetation and, lots of weather activity, which has caused erosion. And then we've got earthquakes that have caused mountain ranges to pop up here and there. And so a lot of these impact points get disturbed or are hidden. Not uncommon now.
Absolutely. And I mean, 70% of the Earth's surface is water, and you need to be a bigger impactor than the depth of the ocean to leave a scar on the ocean floor. So the history of impacts on the Earth is very much muddied by all of these different processes. The ice ages have scoured the surface of the Earth clean. We've got weathering, we've got forests. The Earth's surface is actually an incredibly dynamic place compared to the moon. If you look at the moon, there are many craters of this kind of size, and one of the things that is actually discussed in the articles online about this is whether this could be a venue for people to learn more in preparation for visits to the moon, where we can go to craters, or vice versa, whether we could learn more about craters like this by going to the ones on the moon that are the same size but are pristine. Because we're at a similar location with similar targets in the shooting gallery, but on the Earth, everything gets worn away fairly effectively, whereas on the moon, it stays pretty pristine until something else hits it and weathers it away. The only real way you're going to weather lunar craters, with a few exceptions, is by other things hitting them and muddying the water. There is going to be a lot more to learn about this. It is still relatively new news. The geologists involved won't be going there year-round because it gets really, really cold and really unpleasant in the winter. So there'll be summer expeditions going there trying to learn more about it, getting more and more samples of it, because we don't know many craters that are that old on the Earth.
No,
this is
390 million years. That's a That's a long time back, isn't it? That's over 300 million years beyond the dinosaur impact. So
absolutely.
Pretty impressive.
It's far from the oldest crater on the Earth, but I would argue that we know far more younger craters than we know older craters than this.
Yeah. Didn't they recently say they found the oldest one in Western Australia, was it?
Yeah, and I think that was a little bit controversial, but there was a lot of talk about shatter cones with that one as well.
Yes, there was. I remember that.
You know, we're finding craters more and more, and they tell us about the history of the Earth and the heritage of it. With the really old craters, there's even some arguments that the largest impacts that happened very early on in the Earth's history were actually the seeds of the continents to some degree. There was some amazing work. This is probably actually best part of a decade ago now, but there was great work by Craig O'Neill and his team that were looking at trying to model the initiation of plate tectonics on the Earth. So how did plate tectonics get going? And these incredibly talented geophysicists here in Australia were running models where you start the Earth with no plate tectonics, looking at the interior, looking at how hot it was back then. And if you started the Earth without plate tectonics didn't happen. And what they thought could be the smoking gun was that you had impacts that caused a big impulse of energy and motion in the mantle that triggered a downwelling, which would then trigger an upwelling, and you could get impact-induced plate tectonics, which would then cause these things to maybe even give you the seeds of the continents, of the earliest continents. And that's an awesome story. The videos that they made of their simulations were fabulous. And yeah, it's amazing what more there is still to learn, I guess.
Yeah, absolutely true. And this is another story that's been picked up by all and sundry. You shouldn't have any trouble finding it if you do a search for the Canadian amateur astronomer who was planning his holiday. And the story will pop up just about everywhere, space.com, the Smithsonian Magazine, etc., etc. By now, when you hear this episode or very close to this point in time, the team that made the discovery will be presenting their work at the 88th annual meeting of the Meteorological Society in Germany. I think that's right. I don't know. Anyway, look it up. It's a great yarn. We've had a very rocky program today. Jonti, it's been fascinating the way those stories all dovetailed into each other. And we're at the end. Thank you very much. Nice to see you again.
It's good to be back. Thank you for having me, and hope Fred's enjoying his jaunt.
Chasing a solar eclipse, yes.
It's
indeed.
a hard life, but somebody's got to do it.
Absolutely true. I'm waiting for one to come to me. I only have to wait 2 more years.
2 more years.
Thanks,
and it'll be cloudy. You know it's going to be cloudy.
Oh, yeah, it's probably going to be raining. And I'm giving up a game of golf for it too. All right. Thanks, Jonti. We'll see you soon.
Yeah, it's a pleasure.
Professor Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Don't forget to visit us online while you are waiting for the next episode, spacenutspodcast.com. And have a look around while you're there, visit the shop, etc., etc. And thanks to Hugh in the studio. Couldn't be with us today. Put his home address in Google Maps. We haven't seen him since. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.